Alright, so now that we understand the concept of buffers and we also understand binary data, hexadecimal, and character encodings, we are now ready to get into coding and use the buffer object and write some zeros and ones to our memory. So I am on my terminal right now, navigated to my desktop, and now I'm going to go to the uncc code. Remember, in this folder we're going to save all the code that we're going to write in this course. And for each section, we're going to create a new folder. So for this section, I'm going to create a new folder and I'm going to call it buffers. I'm going to now navigate to that folder and I'm going to open it up in my code editor. And here we go. So I'm going to just create one file here in the buffers folder and I'm going to call it app.js. And here in the file, I'm going to first include the buffer object. So const buffer equals require buffer. Now this buffer object is also available to us globally, so we might not need to do this, but in the docs Node.js says that it's better to explicitly include the object. So I'm going to just do that. All right, so now that I have the buffer object in place, I can go ahead and allocate a piece of my memory aside for myself for my later use. So I'm going to say const maybe memory container equals buffer.alloc. Now using this method, we can allocate a piece of our memory aside for our use. And here we have to specify a value in bytes. So I'm just going to say buffer.alloc 4 bytes. So now if we go back to our concept, by running that buffer.alloc, we are creating this container off of our memory for ourselves. So now we have access to this container and we can write zeros and ones to it. And remember, our length is fixed. So we used 4, so the size of this buffer is 4 bytes or 32 bits. So now we have this container available to us. And also remember that a buffer kind of acts like an array. So we've got all these different elements in it, and each element holds exactly 8 bits. And it's initialized with zeros. So now we have this little thing available to us in our code. So this memory container is that box that we just saw, and the size is 4 bytes. I'm just going to say it here, 4 bytes, okay, or 32 bits. And we already know that each bit is either a 0 or a 1. All right, so now that I have my memory container, I can access its elements just like an array. So I could say element 0 or element 1 or 2 or 3. Right, and 3 is the last index because our size is 4. But let's just quickly first log this memory container and see what we're dealing with. So I'm going to say console.log memory container. All right, so let's just log this amount of memory that we allocated for us and see what we have. So I'm going to go over to my terminal and let me just make it a bit bigger. All right. Now I'm going to just say node app.js, and as you can see here, I get that buffer that I just created. And all the elements are initialized to 0. So this is my first element, my second one, third, and fourth. And each element again holds exactly 8 bits. All right. Now the values are displayed to me in hexadecimal because if you recall, we said this, that if you try to take a look at your memory contents or the binary data of a file, we usually display that in hexadecimal. It's just a convention. It's way easier to display that in hex compared to zeros and ones, but it can easily convert that back and forth. So if we write some stuff here, we can easily just convert that into zeros and ones by just taking a look at that table that we had or using our calculator. All right, so maybe let's first access the first element. So I'm just going to duplicate this log. And in the second log, I'm going to just access maybe the first element. So let's go ahead and log this again. And as you can see here, my first element is just 0, just like here. So the point is that we can now access our elements just like this. And well, now that we have our memory container, we can go on ahead and write data on it. We can now write zeros and ones to this piece of memory that we have allocated for us. So let's do just that. So I'm going to say memory container in the position 0. Let's maybe write 4 ones. So I'm going to write it in hex because, well, again, it's much easier. So I'm going to say F. This F means 4 ones. And let's also, for the next 4 bits, write maybe 4. All right. So this now means that in the first elements of my buffer, go ahead and write this data. Again, this is a hexadecimal number. And if you want to take a look at the zeros and ones, you can just open up your calculator. You can put in that number. And here we can take a look at the contents, which is 4 ones and then 0, 1, and then 0, 0. All right, so I'm writing this amount of bits, this 8 bits, into the first element of my buffer, okay? So now with this in place, I'm going to move my logs down in the bottom. And let's go ahead and log our buffer again. But now we have saved something in our first element. So I'm going to open up the terminal. And I'm going to run my application again. And now we get our buffer, but our first element right now is 4F. Okay. And then we're logging the first element and we're getting 244. Now this is in decimal. So if you try to log each element by itself like this, you're going to get that value in decimal. All right. So just like this, we can go on ahead and write to all of our elements. So element 1, we're going to write maybe 3, 4, and then element 2, let's write maybe B, 6, and then for the last element, let's just write maybe FF. And let's also just log all the elements individually as well. So the second one, the third one, and then the fourth element. So now I'm going to go ahead and log my buffer again. Let me first clear my terminal, and now I'm going to log it. And you can see that now, in this case, my buffer is now completely filled. And here are the values of each element. Now I want to ask you a question, and I want you to think about it for a second. When we're logging the elements, what is the maximum and the minimum possible number that we could get here in the logs? And I mean in decimal. So I want you to go on ahead and think about this for a second, and also make sure to use your programming calculator, because that's going to help you to easily find the answer to that question. All right. So pause the video for a sec and think about what is the maximum and minimum value that each element of our buffer could hold. All right. Hopefully you thought about it for a second. And the answer is that the minimum value in decimal, if you log it, is 0, and the maximum value is 255. But why do you think that's the case? So let me just open up the calculator pretty quick. Now if you go into your programmer calculator, here we can see the first 8 bits. All right, so each element holds exactly 8 bits. So what is the lowest number that each element can hold? Well, if we fill them all with zeros, that is the lowest number. So it's 0, right? But what is the maximum? The maximum is when you change all of these zeros to just ones, like this. So if I change them all to ones, here we can take a look and see that I get FF. But if I change it to decimal, here it's 255. So there's absolutely no way that an element can hold a value that's bigger than 255. So 8 bits, the maximum value that 8 bits can hold in your computer and all the computers in the world is 255. Well, of course, you can use more bits to increase this number. For example, if I just add in one more bit, the number is going to be 500. One more bit is going to be 1000. Maybe a few more bits here, it's 33,000. So the more bits you add, the bigger the number that you can store. But in each element of our buffer, because we're only using 8 bits, that number is 255, all right? So please keep that in mind. And also you can't go negative. If I just set them all to zeros, it means that now this is the lowest number that the buffer can hold, and it's zeros. So this is the concept in the whole computers, all right? This is the same thing in your phone and all the computers in the world, all right? So please keep this in mind. Now you might be saying, okay, does that mean that my memory cannot hold negative values, or does it mean that my memory cannot hold float numbers or things like that? Well, actually it can, but we're not going to talk about it, okay? We've got some stuff here like 2's complements and 1's complements, and with these in place, we could also represent negative numbers in our memory. So there are ways that you can store negative numbers in your buffer as well. So here if I say negative 34, so if I now log this, you're going to see that I saved negative 34, but as my third element, which is DE, I'm getting 222. So we stored -34, but we got 222. What in the world is happening? Is this a bug? Well, it's not. What is happening is that we have these different ways to represent other numbers. We can represent float numbers, we can represent negative numbers in our computers. It's a topic of computer organization and computer architecture, and we're not going to talk about it. But in short, I want to just give you some ideas so that you know that this is not actually a bug and this is how it's supposed to be. So if I go into my calculator again, the number that we see here is 222. Okay, so we stored -34, but we got 222. So if I write that number here, 222, as you can see here, what we have to do is that we have to get the 2's complement of this number. So this is the number that we're getting. And now because we wrote a signed number to these 8 bits, we should now regard it as a signed number. We should now calculate it differently as we would with a normal positive integer. So the most significant bit for us is going to be our sign. So this is going to be the negative value. Again, don't worry about that. The point is that we got to take the 2's complement of this number, and that means that we have to flip all the bits over and then add 1 to it. Okay, so if I flip all the bits, so I'm just going to click on each one of the bits like this. All right, now I'm going to get the number 33, and we just have to add 1 to this number, and then I'm going to get 34. But this is a negative value, all right, because we're storing 222 and our first bit is 1. So this is how we can kind of save negative numbers. If it doesn't make a ton amount of sense to you, please don't sweat it. It doesn't matter. We've got all these different ways to save all different kinds of numbers in our computers. We've got all these different conventions to do that. This is how we can add numbers together, multiply them together in computers using binary. But again, it's a topic of computer architecture, computer organization, and we're not going to talk about it. But I just wanted to point this out. If you take a course in that topic, you're going to learn about all these things. You're going to learn about these logic gates. You're going to learn how to multiply numbers together, and you can end up creating a tiny mini processor for yourself and then be able to create a calculator from scratch. It could be a fun project, but again, it's outside of the scope of this course. But I just wanted to point this out because I know that if you go ahead and play around with this and try to save some negative numbers, you're going to see some weird things, but it's not weird actually, it's expected, and well, that's why. But the point is that each 8 bits, the answer to that question that we asked before, is that it can store a value from 0 up until 255, okay? Because we got 8 bits, and the maximum value is if we flip all the bits to 1, and the lowest value is if we flip all the 1s to 0. So this is the range that we have. And you can easily, again, find the answer by going to your calculator and flip all the first 8 bits to 1s, and you can see that the maximum value right here is 255. Now, I also want to say that this is not a really good way to saving a negative number in your buffer, because as you can see, it could get confusing. The buffer object gives us some methods that are specifically there to help us deal with numbers in our buffer. Now, in the computers, we've got all these different concepts about how we can save numbers in our memory. How can we deal with numbers? For example, saving a negative number or saving a number that is not an integer. What will we do in that case? These are really important concepts in computers, and it's really important to be able to deal with negative numbers. In that case, we can now add numbers together and all that kind of stuff. So we've got some various methods available in the buffers. You would rarely need to use them here in Node.js to just save a number in a buffer. Use some rare cases I can think of, but not really. If you want to save a negative value or a floating point number, just use a variable and not use the buffer object. But if you're dealing with data that is all number, sometimes it could be useful. So we've got these methods. They usually start with write, not just write, because this is for strings and we're going to talk about it in just a bit. But anything that starts really with write, all these methods are for this purpose of writing numbers to our buffer. So if we want to write a negative number to our buffer that is 8 bits, such as -34, we should use this method that is called writeInt8. So with this method, we can say -34 and then the offset, so we're going to write it to that position 2, and now this is much more clear compared to the previous thing. And then here, if we want to log that, instead of just logging the 2, we should also use the correct corresponding method, which is called readInt8. Okay, the exact same thing, so write or read. And here I can just specify my position, which is 2, And now if we go ahead and log this, now we're getting the correct value, which is -34, all right? So we've got these methods. We're going to take a look at them in the documentation. They all start with write and then something. For example, write big int 64. This means that if you want to write an integer that is 64 bits. So now a few of the elements that will add up to the size of 64 will be regarded just as a number. Now, again, it's the exact same thing. We're writing straight zeros and ones, but then later on when we want to read it, we will read it in a good manner. So we are regarding the first 8 bits as a negative number. So also here we are regarding those 8 bits as a negative number. So now we would flip this over and then add 1 to it and then display it. And also when we display it, we're also going to add a negative value before it. But please keep this in mind that if you want to write a big number in your memory, something that's bigger than 8 bits, please use one of these methods and not do it this way. This is just for straight binary data. You want to just specifically say that this bit should be 1 or this bit should be 0 and whatnot. But if you want to deal with numbers, use one of these methods that you have available to you. For example, if you want to write a double number, a number that is not an integer, use one of these. All right, or if you want to write an unsigned number, this U means unsigned, so you can use one of these. Again, to really be able to effectively use these methods, you have to learn about how numbers are stored in your computer. Again, it's a topic of computer organization. It's not something that we're going to talk about. Maybe later on in one of the future sections that I'm going to create, we're going to talk about these things, but not that I know of. I can't really think of a good reason why would you want to do this in a buffer. There are some rare cases again, but not that much really. In those cases, you can just use variables. But in some cases, when the data that you have is just a number and you really want to control it, this could come in handy, but not really. It's not really as common. All right, so I'm just gonna change this back to the previous thing that we had. So 2 equals 0x and then 0, 0, right? And I'm also gonna change this back to just 2. So that's just something that I wanted to point out. And what I'm going to do now is that I'm going to just log my buffer, but just get all the zeros and ones straight out of it. We can easily do that. So I'm just going to say console.log my memory container .toString. And here in the toString, we've got this method on each buffer object. So on each buffer that you create, you have access to this method, which is called toString. But you have to specify how you want to get that. And here you can see my Visual Studio Code. I get a list of all different kinds of encodings and different things that I can just access. So if I say hex, it means to display my whole buffer, but just the hex values. So if I go ahead and log this, here you can see that I get the contents of my buffer, but just the hex values. Well, I have some raw data. I can maybe send this raw data somewhere. So I've got this raw data, and using that toString, you can just grab each one of them and just display them in a nice line like this. So it's no longer an array, and well, you have access to it. Keep in mind that again, you can also loop through the elements of the buffer because it's again like an array. So you can just create a for loop and then loop through it, and then access each element and then modify each element individually maybe. In the real world, the buffers that you're going to create and deal with are much bigger in size, not 4 bytes. Sometimes they have sizes of 16,000 bytes or even more, sometimes 80,000, sometimes 60,000, but it's the same concept. So we're just dealing with a very small buffer to get the concepts, to really get a good feel about it. But I can imagine that this buffer could be much bigger in size, but the concepts, well, are the same thing. All right, so now that you have this good understanding about buffers, I'm going to give you a challenge, all right? So let's go ahead and create a new file here in our directory, and I'm going to just call it challenge.js. All right, so here's the challenge. I'm going to give you some straight binary data, and I want you to go on ahead and write that binary data to your memory. All right, so here's the binary data. I have it somewhere here, so I'm just going to copy it from my other screen, and I'm just going to paste it right here. All right, so this is some zeros and ones, some raw binary data. And what I want you to do is that I want you to go ahead, allocate a piece of your memory to your Node application that is just the right size, okay? So make sure that you don't allocate more than what you need. Allocate just the exact same size. And remember that each number, either 0 or 1, is exactly 1 bit, and also 8 bits is equal to 1 byte, all right? So please go ahead, and write this to your memory. And once you're done, once you have written it into your memory, I want you to go on ahead and log this to your screen using an encoding, using the UTF-8 character encoding, right? So you have that space in your memory, you have this data in it, then I want you to log that onto your screen using a character encoding, well, UTF-8, right? So you use UTF-8 to log this onto your screen and see what you'll get. So please pause the video for a few minutes and think about this problem. You should be able to do this because now you know how to allocate buffers, you know how to write zeros and ones to it, and you also know about that toString method. So you should be able to do this problem. All right, so pause the video now and I'll catch you back in a second. All right, so now I'm going to show you my solution. I also notice here that I have a typo here in the file name, so I'm just going to change it pretty quick. So it should be challenge. All right. And now what I'm going to do first is that I'm going to include the buffer object. So const buffer equals required buffer. And now that I have my buffer, I'm going to allocate a piece of the memory to my Node application. So I'm going to say const, let's just call it maybe buff equals buffer.alloc. Now, what do you think should be the size that we should specify here? Now, if you think about it, here we have to specify the size in bytes. Now, how many bits do we need exactly? If you count all of these, we've got 1, 2, 3, 4, 5, 6. So 6 portions, so 6 times 4, which is 24 bits. Okay, so we're going to need 24 bits. Now, how many bytes is 24 bits? So you just have to divide that by 8, and then the result is 3 bytes, all right? So we're going to need 24 bits exactly, and because we have 24 zeros and ones, and if we divide 24 by 8, the answer is 3. So we should specify 3 right here. So our buffer, the memory container that we're going to have, is going to have exactly 3 bytes. And now that I have this, I'm going to go ahead and write my data to it. So I'm going to say buff in the first element. Here I'm going to write this one. And I'm just going to quickly open up my calculator to calculate these numbers to a hexadecimal, or I can just easily use that table. So the first byte should be this. So I'm going to put 1 here, and then 0, 0, and then 1, and then a few zeros. And let's also make sure that we change our base to base 16. So now we were getting the value in hexadecimal, which is 48. So I'm just going to put that 48 right here. So I'm going to say 0x and then 48. Now for my second element, here I'm going to now specify the next 8 bits. Again, remember each element holds exactly 8 bits, so we'll have to use 2 hexadecimal characters for that. So for the next 8 bits, I'm just going to put it here in my calculator. So it is 0 and then 1, 1, and then 0 and then 1, double 0 and then 1. And the number is 69. So I'm just going to put that number here. And now for the last element, so element with index number 2, this is going to be our last 8 bits. So I'm going to put that here. So it's double 0 and then 1 and then 0 and then 3 zeros and then 1 1, and the number is 21. So I'm going to put that here as well. All right, now that I have written the binary to my buffer, let's go ahead first and log the buffer and make sure that we don't have any zeros or that we're not missing any data. So I'm just going to say console.log and then buffer. And actually it should be buff and not buffer because we named it just buff. All right, now I'm going to go over to my terminal and run the code. So node challenge.js, and here you can see the data. Now, if we had allocated a buffer, but not with the right size, so if we had, instead of 3, if we specify maybe 10, now in this case, we're going to get some bytes that are not filled, which means that we are allocating more space than what we need, and this is not a good practice at all, okay? So you have to make sure to specify the correct size, just the right size that you need. Now, if we also specify something that's less than 3 bytes, for example, only 1 byte, in this case, now we're going to miss some of our data. So we only wrote the first byte, but the second 2 bytes are now discarded. So if we allocate a buffer and we try to write more data than the space that we have available, the rest of the data is just going to be discarded, and it's just like as if you haven't even written that amount of data. So in this case, these 2 lines, if we allocate a buffer with only 1 byte in size, these 2 lines now have no effect whatsoever, all right? they're just going to be discarded. So it's really important to always specify the buffer with the exact number of bytes that you need. In our case, it's 3. Okay. All right, so now that we have the buffer with the exact right size and the data that we need, let's now go ahead and run it through a character encoder and see what we'll get. So I'm going to say buff.toString. I'm going to use the toString method that we have available on all buffer objects. And here we can specify some different things. Now in this challenge, we have to use UTF-8. So I'm going to say UTF and then -8. And now let's go ahead and run the code. And now as you can see, we got the string hi with an exclamation mark afterwards. Now, if you managed to get this string, that means that you did the challenge correctly, and congratulations. So what we did is that we just took some zeros and ones, we just took some raw binary data, we wrote it to our memory, and then we ran it through a character encoding, and we got a meaningful text to us humans. Pretty cool, right? So now we have some raw binary data here. If we want to send this maybe to someone else in another part of the world through our networking technology, we can easily do that using zeros and ones. Or if we want to save it to a flash disk or to our disk, we can easily save this. And we know that we should use a character encoding to make sense out of it. All right, so that's it about our challenge. Now we could have also done this differently. If you have referred to the documentation, you would see some other ways that you can create the buffer out of the exact same thing. So instead of this, we could have, let me just go back to app.js. So here we can just create a buffer, and we can say buffer. Instead of using alloc, we can use the from method, and here we can specify our raw binary data. So the first one is 0x48. Next up we have 69 and then 21. And now if I go ahead and log this buffer, so buff.toString UTF-8. Now if I run app.js, I'll get the exact same string. All right. So you could have also done it this way using the from method. And also notice that you have to specify the correct encoding. So if I specify something else, such as UTF maybe 16, if I specify this one and if I log it now, you can see that I'm getting a character that's from another language. Because in our character encoding, UTF-8, that piece of data means exactly this string, okay? But in another character encoding, we were mapping different sequence of bits to different characters. So those exact same bits mean this character. So please keep that in mind, that going from one encoding to another encoding, you're going to see drastically different things, right? Your data is not going to make sense anymore, okay? Now, back to our discussion about this from. Now, what this does is that it's going to take this data and it's going to automatically figure out how big it should allocate that piece of memory for you, how big that buffer should be. So you don't really have to now care about what size you should specify. You can just say .from and then specify your data, and Node itself will automatically figure out how many bytes you need, and it will allocate that much bytes to you. So you can also do it like this. Now this from is also a little bit faster, but we're not going to talk about it right now. We're going to have a discussion about it in the next video. But the point is that you can also do it this way. Now this from method is actually kind of smart, meaning that it will automatically try to figure out what is this thing that you specify to it, and it'll try to create a buffer out of it. And you can either specify an array like this, that is kind of like the scheme of the buffer. So each element of that array that you're going to specify will correspond to that element of the buffer with that same index. And you can either specify hexadecimal values here, or you can maybe specify a decimal, but you have to make sure to stick to that 0 to 255 range. So you can also do it this way. Now you don't have to specify an array that each element will correspond to an element of the buffer with that same index. You don't always have to do this. You can also just specify a string here, and then as the second argument specify how you want that string to be interpreted. So let me just do this pretty quick. Actually, let me first comment this memory container thing, because let's just minimize the amount of logs that we're getting. So I'm gonna comment this whole thing, and I'm gonna copy paste this, and I'm also gonna comment this one like this. Now here, I'm going to, instead of doing it this way, I'm just going to specify it in a string as a raw data. So now I don't have to specify each element at a time, and also I don't need these commas and these 0x's and so forth. So I can just simply specify my value like this, all the hex values. And here in the second arguments, here I can just say hex. So now I'm telling this buffer object to take this data, which is a hex data, and create a buffer out of it. And then again, also automatically figure out how many bytes it needs to store this amount of data. And this is the exact same thing as before. So 48, it's here, and then 69, it's here, and then 21, which is right here. So if I go ahead and run this, so node app.js, I'll get the exact same thing. So now if you are getting some raw binary data, you can just put it here as a string and specify the hex thing right here, and then it will automatically do the same thing. So now you don't have to just create an array and then specify every single element and whatnot. So this is much simpler to do compared to this one. Now here in the from, you can also specify some other encodings, such as a character encoding. And in that case, you can just specify your string, maybe string like this, and then here you have to specify now a character encoding. You've got access to a few of them, like Latin1 or UTF-8. Now these two, UTF-8 and UTF-8, they're the same thing, it's just an alias. So here you can also do it this way. So what this means is that the buffer object is going to take this string, and then it's going to convert it into zeros and ones using this UTF-8 and figure out how many bytes it needs to create that buffer, and then it'll create that buffer and put those zeros and ones in that buffer. The zeros and ones that it's going to end up with after converting this string to zeros and ones using this encoding. Now if we run this, well, we're going to get just simply string, but if you just log the buffer as it is, you're going to get the buffer like that. All right. And if I just use the previous thing that we had, which is hi with an exclamation mark, now here we're going to get the exact same values as we had before, 48, 69, and then 21. So this could also come in handy when you are trying to create a buffer out of a string. You can just do it this way, and you don't have to maybe go into an ASCII table or something and try to manually figure out what's the hex value for each character. You can just automatically do this and it will work just fine. And also just a quick point about this UTF-8. If you're wondering to know if there is a list of this UTF-8, same thing as there's a list for that ASCII thing, that we can just run man ASCII and see the whole list. Well, there's this website that I just found out. It's called symbol without the o.cc. So if we go to this website, symbl.cc, link will also be in the resource section of this video. Here you can see the whole list of all the Unicode characters. Now, I'm not sure if it has every single one of the characters in Unicode defined here, but it's one heck of a list, I tell you that. And, well, actually, if you scroll down all the way here, it says that all symbol names are official Unicode names, and all the code points are listed by the Unicode standard. So it should have all the characters in the Unicode, and, well, it's Unicode standard. Now, a code point, you're going to hear this a lot. It's just one of those technical terms that sound much more complicated than what they really are. It's just a number. So character S has that 115, we just call that 115 its code points. Well, again, it's just a number, but well, in character sets, we just call them code points. All right, so if you just want to see the whole list, you can just click on here in symbols, and then here you can see the whole list. Here, for example, that S, and here's the code point for that S. It's 73 in hexadecimal, but this is actually that 115. So if I open up my calculator, and if I just put that 73 right here, the code point, and I change it to decimal, I'm going to see that 115. So code points are just numbers. Just keep that in mind, please. And they also start with something before the actual number, for example, U plus in this case, and the number, but in hexadecimal. So don't be confused when you hear this code point thing. It's just a number, okay? Now here, if you go into the encoding section, you can see that in different encodings, that in UTF-8, this is the hex value, this is the decimal value, and also this is the binary. So UTF-8, if it wants to store character S, it's going to store this binary in your memory or in a file or anywhere else. Now if you go back to this symbol, here you can see a whole lot of characters, thousands of characters, tens of thousands of characters. You can see Greek letters, Armenian letters, Hebrew, and if you just scroll down, you're going to see a whole lot of characters, a lot of which I have no idea what they are, but here you can see this whole list, and you can just try to encode or decode each one of them using UTF-8. You can just use that character encoding, use the buffer object to just encode and decode these things. Now, for example, maybe this one, and this is, I have no idea what this character is, but here if you go into the encoding, you can just take this hex value and you can just give it to the buffer. So here, if I put that here, so I'm going to actually duplicate this. If I put that hex value here and I just remove all the extra spaces, here if I specify hex and then log this, let me also comment the previous two lines. So buff.toString using UTF-8. And now if I go ahead and log this, you can see that I get that character. And this is the exact character that we saw. Well, I'm not sure if it's the exact one, because it doesn't look similar, but it should be the same thing. I'm not sure about this language. Maybe we have different ways to show it. Maybe it's a different font. I don't know. But it should be the same thing, unless there's a bug somewhere and this is not the correct hex value. But it's the same thing. And you can see that UTF-8, when it tries to save this character, it will use this binary. And actually, if you try to search for these characters in your URL, you're not going to see that in your URL. Okay, so you're seeing it right here. But if I open up the developer tools and try to see the exact URL that was sent, just gonna make it a bit bigger. Here, if I go into the network tab, I'm just gonna do a quick refresh. In the first thing right here in the query, this is what we search for. You can see that exact hex value, E0, A4, and 9B. Okay, so in URLs, here the binary value is being transferred. Hex in this case, but you know that hex is just binary, right? Each character is just 4 zeros and 1s. So URLs don't understand these characters. They only understand ASCII characters, which is only about 100 characters. So in URLs, if you try to specify anything that is not an ASCII, it'll try to send the binary instead. And then in your node code, maybe you can just grab this binary and then run a character encoding on top of it, such as UTF-8, and then you're going to get the character, okay? Anyway, I just wanted to also show you this website that you can just take a look at all the characters, and you can take a look here at the encoding in UTF-8 and UTF-16 and different kinds of encodings that we have, and you can also see the binary. So again, here hopefully you can see why it's always important to specify your encoding, because different zeros and ones mean different characters in different encodings. Alright, so that's it about this video, and in the next one we're going to allocate some huge buffers and then monitor our resource usage and see what exactly is happening in our operating system. So I will see you in the next one.